My name is Nurit Haspel, and I'm an assistant professor in the computer science department at UMass Boston. And today I'm going to present a case study for the use of molecular dynamics simulations in the conformational exploration of two peptides and their hybrid polymer conjugates. And this work is done in collaboration with a group of colleagues from the Polytechnic University of Catalonia in Barcelona, Spain. And it actually ties to the many applications that MD simulations have in structural bioinformatics. It's actually a very useful tool for investigating the short-term dynamics of proteins and other big molecules. Among the things that we can extract from MD simulations are knowledge about atomic interactions, performing limited conformational search, learning about the structural stability, modeling the structure of macromolecules, extracting thermodynamical properties, etc. The advantages are that MD simulations can allow us an atomistic view and a very detailed analysis of the structure and dynamics of macromolecules, which are very hard to see in lab, because a lot of times the dynamics is very hard to catch experimentally, and we can actually have like a zoom into the structure. What you see here in the picture is a snapshot of an MD simulation of a small protein, one of the examples that I'm going to present today. You can see the water molecules surrounding the protein, and the purple spheres here are ions that we use for the simulations. So we can actually have this trajectory that represents the short-term dynamics of this molecule, and we can stop it at any moment and take a snapshot of what the molecule looks like in its natural environment under physiological conditions. The big disadvantage of molecular dynamics simulations is that they're computationally expensive, as you probably know. And since we're talking about quite big systems, which contain at least a few tens of thousands of atoms, if not more than that, including the solvents, then even using supercomputer systems and highly scalable molecular dynamics programs, we're still very limited in the amount of time that we can simulate when we're talking about big molecules. So we can only simulate in today's computational capabilities up to a few microseconds, maybe, of dynamics. Also, since MD simulations are depending on the initial conditions of the system, we have to be very cautious in the way that we model the systems. So in this particular work, we want to elucidate the conformational preferences of two particular systems, which are made of peptides that form amyloids in vivo. One of them is arginine vasopressin, and the other one is called neuromedin K. So what we did in this work is to test the conformational properties, the dynamical properties of these peptides when they were conjugated, linked to polyester chains. So it's actually some sort of a hybrid material that we generated, and we wanted to test its properties. So what we did is to simulate how these peptides would look like when they are linked covalently to a polyester chain, to a polylactic acid chain. And we investigated the conformational properties of these peptides when they stand alone in solvent and when they're linked to their polyester chains using MD simulations. And we compared the properties of the isolated peptides and the conjugated materials in order to see what we can do with them. So the study of hybrid materials is actually quite a heavily researched area in the last few years. And what it is, it's actually what happens when we combine the different types of molecules to generate a new kind of chimeric compound that has the property not only of its original components, but also some new and interesting properties. Okay, and we can investigate the conformational profiles and other properties of these hybrid compounds and see how their binding affinity, their activity, their stability are affected by this conjugation. A well-known example of a hybrid material would be click chemistry, which is an area that's been very popular in the last few years, which is what happens if you take some scaffold molecule and you actually plant on it several other molecules. And what you get is a new molecule that has the properties of all of these planted molecules and then some more. So you can actually do a lot of nice things with it. And what you see here in this picture is an example of what happens if you take a small peptide and a polymer and you link them together covalently, you get a new molecule that is actually a chimeric compound, which might have different properties from its original molecules. So in this study, this is exactly what we're doing. We're taking peptides, a little bit longer than this one, but this is just for illustration purposes, and a polymer, and we try to combine them together and see what we get.